Your reality might be less solid than you think. We are about to take a deep dive into the strangest glitches in our universe, from cosmic anomalies that break physics to quirks of human memory that feel like programming errors. This journey will show you the evidence that our existence might be far stranger than any science fiction. You will walk away with a completely new perspective on the nature of reality itself. We will explore why an entire generation misremembers a children's book and what a single mysterious radio signal from deep space could mean. What is the one unexplained event you have always wondered about? One of the most compelling arguments for a glitch in reality is not found in a telescope but inside our own minds. It is a phenomenon so widespread and bizarre that it has earned its own name, the Mandela Effect. This is not about a single person misremembering a detail. It is about thousands, sometimes millions, of people sharing the exact same incorrect memory, with a conviction so strong it feels like a fact. The name itself comes from the most famous case. Many people vividly recall news reports of Nelson Mandela dying in prison in the 1980s. They remember the funeral, the mourning, the political fallout. The only problem is Nelson Mandela did not die in prison. He was released, became president of South Africa, and passed away in 2013. So where did this powerful collective memory come from? Another classic example involves a beloved children's book series. Ask anyone who grew up with them, and they will likely tell you it was spelled Berenstain Bears with an E-I-N. But pull a book off the shelf and the cover clearly reads Berenstain with an I-N. For many, this feels like a direct change, a correction to reality they never authorized. The list goes on. The famous line from Star Wars is not "Luke, I am your father," but the far less personal "No, I am your father." The Monopoly man never had a monocle. And the Fruit of the Loom logo never featured a cornucopia despite countless people sketching it from memory. These are not simple mistakes. They are shared, specific, and emotionally charged. So what is happening? One theory suggests we are brushing against parallel realities. In this view, our consciousness is somehow shifting between very similar timelines, and we carry memories from a version of history where these details were different. Another, more technological explanation posits that if our reality is a simulation, the Mandela Effect could be a data corruption error, a bug in the code that manifests as inconsistent memories across the user base. There are, of course, psychological explanations involving false memory and confabulation, where our brains fill in gaps with plausible details that then spread socially. But even these explanations struggle with the sheer scale and specificity of the shared errors. The Mandela Effect forces a strange question. Is the glitch in our perception, or is it in the world we are perceiving? It suggests that the fabric of our shared experience might be thinner and more malleable than we ever assumed. And if our collective memory can be so convincingly wrong about something as simple as a cartoon bear's name, it makes you wonder what else we might have misremembered, or what else might have quietly changed without us noticing. The unsettling feeling of a misremembered past points toward a glitch in perception. But what if the glitch is not in our minds, but in the very rules of the universe itself? To find that answer, we must shrink our perspective down to the smallest possible scale, to the bizarre and counterintuitive world of quantum mechanics. Here, the solid, predictable reality we experience every day completely falls apart. At this level, particles like electrons and photons do not behave like tiny billiard balls. Instead, they exist in a state called superposition. This means a single particle can be in multiple places or have multiple properties all at the same time. It is not here or there. It is both here and there simultaneously until something forces it to choose. The most famous demonstration of this strangeness is the double-slit experiment. Imagine a barrier with two thin, parallel slits in it. You fire a stream of particles like electrons at this barrier. If particles were just little solid balls, you would expect them to go through one slit or the other and create two distinct bands on a detector screen behind the barrier. But that is not what happens. Instead, the particles create an interference pattern, a series of light and dark bands, as if they were waves that passed through both slits at once and rippled into each other. This alone is strange enough, but the experiment gets weirder. When scientists place a detector to observe which slit each individual electron actually goes through, the behavior changes instantly. The interference pattern vanishes. The electrons start behaving like proper little particles again, creating just two bands on the screen. It is as if the particle knows it is being watched and decides to act differently. This is the observer effect in its most literal form. The simple act of looking, of measuring, seems to force a particle to collapse from a blurry cloud of possibilities into a single, definite reality. This blurs a line we thought was absolute, the line between the objective world out there and our subjective observation of it. It suggests that at its most fundamental level, the universe does not have a single, fixed state waiting to be discovered. Instead, it exists as a tapestry of probabilities, and it only settles on a specific outcome when an interaction occurs, when something or someone looks. In a very real sense, this looks less like the unfolding of predetermined events and more like a cosmic system rendering a result only when it needs to, when a user makes a query. If the bedrock of physical reality operates on these rules, then the solidity of the world around us is not a given. It is a consensus moment by moment, born from an endless cascade of quantum decisions. Quantum mechanics paints a picture of a universe built on probability, a system that seems to render outcomes on demand. This leads to one of the most profound and unsettling frameworks for understanding all these glitches, the simulation hypothesis. What if our entire universe, from the vastness of galaxies to the quirks of your memory, is not base reality, but an incredibly sophisticated digital construct? The idea is not new, but it has gained startling traction in our digital age. Philosopher Nick Bostrom formalized a compelling argument for it. He suggests that if a civilization ever reaches a post-human stage, capable of immense computing power, it would likely run vast numbers of detailed ancestor simulations, recreations of their own history. If that is true, then the number of simulated minds would vastly outnumber the minds in the original reality. Therefore, statistically, we are far more likely to be one of those simulations than an original being. Tech figures like Elon Musk have echoed this, pointing out the incredible pace of our own technological advancement. From simple pixels to immersive virtual worlds in just decades, where might we be in 1,000 years? The logical endpoint seems to be indistinguishable simulation. So where might we find evidence or hints of this digital substrate? Some point to the fundamental limits of our reality. At the smallest possible scale, the Planck length, space itself appears to be granular. It cannot be divided infinitely, much like a digital image breaks down into individual pixels when you zoom in too far. This pixelation of spacetime could be seen as the resolution limit of the simulation. Then there is the mathematical fine-tuning of the universe. The fundamental constants of physics, like the strength of gravity or the mass of an electron, are perfectly balanced to allow for stars, planets, and life. Alter any one by a fraction, and the universe would be a barren void. From a simulation perspective, this fine-tuning looks less like a lucky accident and more like intentional parameters, settings carefully dialed in by a programmer to enable a complex and interesting simulation. This framework provides a startlingly elegant explanation for the glitches we have explored. The Mandela Effect becomes a data corruption error, a slight mismatch between memory files and world state. Quantum superposition and the observer effect are not mysteries, but simply how the simulation optimizes processing power, only calculating the precise details of a quantum system when a conscious observer looks at it to save on computational resources. Even cosmic anomalies could be seen as rendering errors or unfinished code at the edges of the simulated map. If we are living inside a simulation, then bugs, inconsistencies, and glitches are not just possible, they are inevitable. No code is perfect. The real question then shifts. If this is a simulation, who is running it? And more importantly, why are we characters in an ancestor simulation, a science project, or perhaps something else entirely? The simulation hypothesis is a grand, mind-bending idea, but the evidence for a glitchy reality is not always so philosophical. Sometimes it is measured in millimeters per second squared. This brings us to one of the most stubborn puzzles in modern space exploration, the Pioneer anomaly. In the early 1970s, NASA launched two pioneering spacecraft, Pioneer 10 and Pioneer 11. Their missions were monumental: to be the first human-made objects to travel through the asteroid belt, swing by Jupiter, and then continue on into the endless dark. For decades, they dutifully phoned home, their faint radio signals carrying priceless data across billions of miles. But as scientists tracked their journeys, something was off. Both spacecraft were slowing down, not from hitting anything, not from a gravitational tug of a hidden planet, but in a way that made no sense. Their trajectories were deviating from the precise predictions of Newtonian and Einsteinian physics by a tiny, constant amount. It was an almost imperceptible drift, an extra deceleration toward the Sun equivalent to about 1/10 billionth of the gravity you feel on Earth. To put that in perspective, it is like expecting a car to coast for 1,000 miles and finding it stopped just 1 inch short. A minuscule error, but in the pristine, predictable vacuum of deep space where every force is accounted for, a minuscule error is a screaming alarm. For over 30 years, this anomaly haunted physicists. Was it a flaw in our understanding of gravity itself? Did it point to dark matter exerting an unseen pull, or perhaps to new physics beyond Einstein's theories? The spacecraft became the subjects of an epic scientific detective story, with researchers combing through decades of old data and engineering documents, searching for a culprit. The eventual answer was surprisingly mundane, yet brilliant. A team realized that the spacecraft's nuclear power sources generated heat. This heat radiated off the craft's surfaces, but not perfectly evenly. A tiny, anisotropic push from this thermal radiation pressure, mostly from the heat emitted by the electronics boxes at the back of the craft, was acting as a constant, gentle brake. Once this effect was meticulously modeled and subtracted, the anomaly vanished. The case was closed, but its legacy is profound. For decades, the Pioneer anomaly was a verified, measurable glitch in the system. It was a discrepancy between what our laws of physics said should happen and what was actually happening in the real, outer universe. It proved that even with our most advanced models, reality could throw a curveball, a persistent, data-driven mystery that resisted explanation. It served as a humbling reminder that our map of the cosmos is not yet complete, and that sometimes the signal of a fundamental discovery and the signature of a simple engineering quirk can look exactly the same. The Pioneer anomaly was solved, a glitch traced to a mundane source, but another, even stranger gravitational puzzle remains wide open, one that happens in our own cosmic backyard. This is the flyby anomaly. When scientists send a spacecraft on a long journey to the outer planets, they often use a technique called a gravity assist. They slingshot the craft past Earth, using our planet's gravity as a free boost of speed, like a stone skipping off a moving car. The physics of this maneuver is exquisitely precise. We can calculate, down to the millimeter per second, exactly how much velocity the spacecraft should gain or lose as it whips around our world, except sometimes we are wrong. And not by a little. The discrepancies are huge and inexplicable. Take the Galileo probe launched toward Jupiter in 1990. When it swung by Earth for a gravity assist, it gained speed. But it gained just a bit more speed than our best models predicted, an excess of about 3.9 millimeters per second. That might sound trivial, but in the high-stakes game of orbital mechanics, where a tiny error can mean missing a planet by millions of miles, it is a massive red flag. The same thing happened in reverse with the Rosetta spacecraft bound for a comet. During its Earth flyby in 2005, it experienced an unexplained loss of speed of about 1.8 millimeters per second. These are not measurement errors. These are real, persistent deviations from the fundamental laws of motion as we understand them. Think of it like this. You throw a ball against a wall, knowing exactly its speed and the angle. You can predict precisely how it will bounce back. Now imagine you do this, and the ball returns consistently faster or slower than your calculations every single time under perfect conditions. That is the essence of the flyby anomaly. It is as if gravity itself is momentarily glitching during these high-speed planetary encounters. So what could possibly be causing it? The theories are as fascinating as the mystery itself. Some scientists have proposed it could be an interaction with dark matter. Perhaps a halo of this invisible substance surrounds Earth, and its subtle gravitational drag or push tweaks the spacecraft's speed in a way we have not accounted for. Others look to our own planet, suggesting unmodeled effects from Earth's rotation, its uneven gravitational field, or even the subtle influence of ocean tides and atmospheric drag at very high altitudes. There is even a more radical idea that this could be a sign of new physics, a hint that our equations for gravity, which work so perfectly on large scales and in most situations, need a tiny adjustment for objects moving in a specific way through a planet's gravitational field. Decades after it was first noticed, the flyby anomaly is not solved. It persists as a nagging inconsistency in the data, a reminder that even the most well-trodden paths through our solar system can hold surprises. Each unscheduled gain or loss of speed is a whisper from the universe, suggesting that the rules of the game we think we have mastered might still have a few secret clauses we have not yet read. Gravity's strange behavior during planetary flybys hints at hidden rules, but there are two far greater mysteries warping the cosmos itself. They are called dark matter and dark energy, and they are not just puzzles. They are the overwhelming majority of everything that exists. Think of our universe as a complex simulation, a grand piece of cosmic software. For it to run smoothly, the code must define how matter interacts, how gravity works, and how the whole system expands over time. Our current understanding of physics is that code. But dark matter and dark energy are like massive, glaring error messages, showing us that our code is missing about 95% of the necessary instructions. Let us start with dark matter. In the 1930s, astronomer Fritz Zwicky was studying a cluster of galaxies. He realized the galaxies were moving far too quickly. The visible matter in the cluster, all the stars and gas we could see, did not provide nearly enough gravitational glue to hold the cluster together. At those speeds, the galaxies should have flown apart long ago. Something invisible, something with immense gravity, was holding everything together. He called it Dunkel Materie, dark matter. The evidence has only grown stronger. Look at a single spiral galaxy like our Milky Way. Stars on the outer edges orbit the galactic center at roughly the same speed as stars closer in. This makes no sense according to Newton's laws. In our solar system, planets farther from the Sun orbit much more slowly. For a galaxy to have this flat rotation curve, it must be embedded in a huge, invisible halo of matter, a gravitational scaffold that we cannot see. We know dark matter is there because of what it does, not what it is. It has gravity, but it does not emit, absorb, or reflect light. It is utterly dark. It passes right through normal matter and through itself. We have built incredibly sensitive detectors deep underground, hoping to catch a single, fleeting interaction of a dark matter particle, but so far, nothing. It is as if the universe is governed by a force we can measure but never directly witness, a ghost in the cosmic machine. Then there is dark energy, which is even stranger. In the late 1990s, two teams of astronomers made a discovery that won them the Nobel Prize. They were measuring the distances to extremely far away supernovae, using them as cosmic mile markers to see how the expansion of the universe has changed over time. Everyone expected to find that the expansion was slowing down, gradually coasting to a halt under the pull of gravity. Instead, they found the opposite. The expansion of the universe is speeding up. Something is pushing galaxies apart from each other with ever-increasing force. That something is dark energy. It is not a clump of matter, but a property of space itself. Empty space, according to this finding, is not empty at all. It contains a latent energy that causes a repulsive gravity, an anti-gravity force that is stretching the very fabric of the cosmos. Think of it like this: if the universe is a simulation, dark matter is the hidden code that structures the galaxies, the invisible framework that keeps everything from flying apart. Dark energy is the background setting that controls the expansion rate of the entire program, a force we did not even know was in the settings menu, and it is set to accelerate. Together, they compose about 68% dark energy and 27% dark matter. The ordinary matter that makes up stars, planets, and us, everything we have ever seen or touched, accounts for just 5% of the total cosmic budget. So what are these phenomena from a glitch perspective? They could be the ultimate signs that our model of reality is fundamentally incomplete. Our equations for gravity, which work perfectly in our solar system, may simply break down on the scale of galaxies and the universe. It is like using the physics of a flowing stream to try and model a tsunami. The scale is so different that the rules change. Alternatively, if our reality is a construct, dark matter and dark energy could be artifacts of the simulation's underlying architecture. Dark matter might be the gravitational influence of background processes running on the cosmic computer, code that affects the simulation but is not part of the rendered visual output. Dark energy could be a programming parameter, a value like the cosmological constant, that was set at the beginning to ensure the simulation expands and does not collapse in on itself. We are left staring at the universe's greatest mystery, knowing that most of it is made of stuff we cannot detect, driven by a force we do not understand. These are not small gaps in our knowledge, they are yawning chasms in reality's map. They tell us in no uncertain terms that we are still beginners reading the first page of a cosmic instruction manual, and the rest of the pages are written in a language we have not yet deciphered. While dark matter and dark energy represent a fundamental gap in our cosmic code, there is another type of glitch that is far more direct, a single, screaming blip of data that arrived one quiet summer night. It is known as the wow signal, and it remains one of the most compelling and frustrating mysteries in the search for extraterrestrial intelligence. On August 15, 1977, the Big Ear radio telescope at Ohio State University was performing its routine scan of the sky, listening to the static hiss of the cosmos. The data was printed out on long sheets of paper with columns of letters and numbers representing signal strength. For the most part, the printout was a monotonous sequence of zeros and ones, the background noise of the universe. Then at 10:16 that evening, something extraordinary happened. For 72 seconds, the telescope's receiver locked onto a powerful, narrowband radio signal. It was not random noise. It was a clean, focused transmission at the specific frequency of 1420 MHz, a frequency that is naturally quiet because it is protected from human broadcasting, a band where scientists had hypothesized an alien civilization might choose to broadcast. The signal rose in intensity to a peak and then faded away as the telescope's fixed field of view moved past its source in the constellation Sagittarius. When volunteer astronomer Jerry Amon reviewed the data printout the next day, he was stunned. Circling the alphanumeric sequence that represented the signal's unprecedented strength, he simply wrote, "Wow." In the margin, the name and the mystery were born. That annotation captured the sheer, electrifying shock of the moment. Here was a signal that perfectly matched the predicted signature of an artificial interstellar transmission. It was not a satellite, not a passing aircraft, not any known natural phenomenon. It was a 72-second shout into the cosmic silence, and then nothing. The immediate reaction was to find it again. If it was a real transmission from a distant star, it should repeat as Earth's rotation brought that patch of sky back into view. Astronomers pointed telescopes at that exact spot again and again for decades. They scanned the same frequency and nearby frequencies. They used more powerful instruments. The result was total silence. The wow signal never repeated, not once. In the years since, scientists have proposed natural explanations. One suggested it was a signal reflected off space debris. Another, more recent theory pointed to the passage of a comet that was not known at the time, suggesting its hydrogen cloud could have emitted a similar signal. But these explanations have significant problems, including the fact that comets do not typically produce such a strong, narrowband signal, and the specific frequency of the wow signal makes a natural origin deeply puzzling. Which leaves us with the tantalizing, unresolved possibilities. Was it a one-time burst from a distant civilization, a cosmic flare of communication we happened to catch for a fleeting moment? Could it have been a targeted beacon that swept past our solar system, a lighthouse beam we briefly stood in? Or, from the perspective of a glitch in reality, was it something else entirely? A system ping from the cosmic machinery itself, a momentary burst of diagnostic data from the underlying processes of the simulation, a blip of pure information with no intended recipient, accidentally intercepted by a lonely telescope on a small blue planet. The wow signal stands as a singular event, a data point of one. It is the ultimate cosmic tease, a message that arrived without a repeat, without context, and without any hope of a reply. It proves that the universe is capable of producing perfect, mysterious signals that defy explanation. And it leaves us forever wondering what or who said hello that night and why they never spoke again. The wow signal was a fleeting, mysterious shout, but there is another cosmic anomaly that behaves more like a system struggling to render an object correctly, a star that simply does not act like a star should. Its official name is KIC 8462852, but astronomers know it as Tabby's star, named after the scientist who first highlighted its strangeness, Tabitha Boyajian. Located about 1,500 light-years away in the constellation Cygnus, this otherwise ordinary star became the center of one of the biggest astronomical mysteries of the last decade, all because of how its light flickered. Our primary tool for finding planets around distant stars is the transit method. We watch for a star's light to dip ever so slightly and regularly, a telltale sign of an orbiting planet passing in front of it. The Kepler Space Telescope observed hundreds of thousands of stars this way, and their light curves usually show clean, predictable, repeating patterns. Tabby's star's light curve, however, looked broken. Instead of small, periodic dips, it exhibited dramatic, irregular dimming events. The star's brightness would plummet by up to 22%, a staggering amount. For comparison, a Jupiter-sized planet would block only about 1% of a star's light. These were not neat, symmetrical dips either. They were jagged, asymmetric, and completely aperiodic with no repeating rhythm. Sometimes the star would dim for days, other times for weeks, in chaotic, deep troughs that looked nothing like the signature of any known planet or even a swarm of planets. Faced with this bizarre data, scientists had to consider every possibility, including the most extraordinary. The wildest and most famous hypothesis was that we were seeing evidence of alien megastructures. Specifically, the idea of a Dyson sphere, or more likely, a Dyson swarm. This is a hypothetical concept where an advanced civilization constructs a vast array of energy-collecting satellites or platforms orbiting their star, capturing a significant portion of its light to power their society. Such a structure would not be a solid shell, but a messy, uneven swarm blocking light in irregular, non-repeating patterns, exactly like what was observed. For a time, Tabby's star became the best candidate in the galaxy for evidence of a Type II civilization on the Kardashev scale, a civilization capable of harnessing the total energy output of its star. The idea was not that astronomers believed this was definitely the answer, but that the signal was so weird it forced them to rule out the impossible, and this was the last impossible thing left. Of course, extraordinary claims require extraordinary evidence, and the hunt for a natural explanation intensified. Subsequent studies have proposed more conventional, if still unusual, causes. The leading theory now involves swarms of exocomets, vast clouds of icy fragments and dust, perhaps from a recently shattered giant comet or a collision in a distant asteroid belt. This orbiting debris field with its clumps and tails could create the irregular, deep dimming patterns. Other ideas include intrinsic stellar variability, though the star itself appears stable, or a vast, warped ringed planet trailing immense clouds of dust. Yet each of these natural explanations has its own difficulties in perfectly matching the observed data. The comet swarm theory, for instance, requires an implausibly large number of giant comets all transiting at once, a statistical oddity in itself. So why does this feel like a glitch? Imagine you are monitoring a vast simulation of a galaxy. Every star is a point of light governed by a set of predictable algorithms for brightness and behavior. Most follow their code perfectly, then you come across Tabby's star. Its light output flickers erratically, dipping in ways your stellar models cannot process. It is not following the standard planet transit subroutine. It is not matching the variable star algorithm. From your perspective within the simulation, it looks like a rendering error, an object whose graphical properties are buggy, flickering in and out of view as the system struggles to calculate what should be displayed. The data stream from this one star is corrupted, inconsistent, and defies the clean logic of the rest of the program. Whether the cause is a natural cosmic catastrophe like a comet apocalypse or something else entirely, Tabby's star stands as a persistent anomaly. It is a reminder that even the most constant fixtures in our sky, the stars themselves, can behave in ways that challenge our entire understanding of what is possible, acting less like predictable cosmic engines and more like flickering pixels in an imperfect display. Tabby's star flickers like a faulty pixel, a single anomaly in a vast cosmic display. But what if the strangest glitch is not a single star acting up, but a profound and universal silence? This is the heart of the Fermi paradox, a contradiction so deep it feels like a bug in the logic of the universe itself. The numbers are overwhelmingly in favor of life. Our galaxy, the Milky Way, contains hundreds of billions of stars. A large fraction of those have planets, and billions of those planets are in the habitable zone where liquid water could exist. Life emerged on Earth relatively quickly once conditions were right, suggesting it might be a common process. And given the galaxy is over 13 billion years old, there has been more than enough time for intelligent civilizations to arise, spread, and make their presence known. The universe should be teeming, buzzing with activity, yet when we listen, all we hear is static. When we look, we see no signs of great engineering, no interstellar traffic, no welcome messages. The silence is deafening. Where is everybody? This question, famously posed by physicist Enrico Fermi, is the paradox. It is the glaring gap between expectation and observation, a glitch in our cosmic sociology. One terrifying solution is the Great Filter. This idea suggests that there is a barrier, an evolutionary or technological step that is extremely difficult to overcome, and it lies somewhere on the path between non-existence and a galaxy-spanning civilization. The frightening part is we do not know if we have already passed it or if it still lies ahead of us. If the filter is behind us, perhaps the step from simple life to complex, multicellular life is astronomically rare. That would make us incredibly lucky but alone. If the filter is ahead of us, it means most civilizations destroy themselves before they can colonize the stars, through nuclear war, environmental collapse, or a technology we have not yet invented. Our silence would then be a preview of a common cosmic fate. Another, more peaceful idea is the zoo hypothesis. It proposes that advanced civilizations are indeed out there, and they are aware of us, but they have chosen to observe us without interference, like we observe animals in a protected wildlife preserve. They are deliberately maintaining radio silence to allow our civilization to develop naturally, to avoid cultural contamination. In this view, the Great Silence is not a bug, it is a policy, a prime directive enforced across the galaxy. From the simulation perspective, the Fermi paradox takes on a new layer. If we are in a simulated reality, the silence could be a programmed feature. Perhaps the simulation is not rendering other civilizations because they are not relevant to the experience of the simulated beings inside it, us. Or maybe interstellar communication is simply not part of the simulation's rule set, a limitation built into the code to save processing power or to keep the experiment contained. Alternatively, the silence could be a bug in the interstellar communication protocols themselves. What if the method we use, listening for radio waves, is hopelessly primitive? An advanced civilization might have moved on to neutrino communication, quantum entanglement, or something we cannot yet conceive, leaving our radio telescopes listening to an abandoned channel. Or perhaps they are communicating, but in a way our minds are not equipped to perceive, like an ant trying to understand the internet. The eerie quiet of the cosmos might be the ultimate glitch, a sign that our assumptions about life, intelligence, and communication are fundamentally flawed. It forces us to confront a humbling possibility. We may not be special, but we might be early, or we might be alone, or we might be living in a universe where the rules for making contact were written by a programmer with reasons we cannot possibly fathom. The silence is not empty, it is full of questions, and every one of them asks us to reconsider our place in the grand scheme of things. The profound silence of the cosmos is not always absolute. Sometimes it is punctuated by screams. These are not the slow, drawn-out signals we hope for, but violent, explosive bursts of raw energy that appear and vanish in the blink of an eye. They are called fast radio bursts, and in their fleeting, brilliant existence, they might represent the most energetic glitches we have ever detected. An FRB, or fast radio burst, is exactly what it sounds like. It is a pulse of radio waves, a flash of cosmic static that travels across billions of light years to reach our telescopes. What makes them extraordinary is their intensity and their brevity. In just a few milliseconds, a single burst can release more energy than our sun emits over 80 years. Then it is gone. For a long time, astronomers debated if these were even real cosmic events or just terrestrial interference, a glitch in our own equipment. But the evidence became undeniable. These were signals from deep space, and their source had to be cataclysmic. The first major clue came when scientists found a repeater. While most FRBs are one-off events, a single flash from the void, one source was caught firing off multiple bursts again and again from the same location. This ruled out any theory involving a single destructive explosion, like a star blowing itself apart. Whatever was making these bursts was surviving the process, like a cosmic lighthouse that could flash with unimaginable power, go dark, and then flash again years later. So what natural cosmic engine could possibly produce such staggering, focused energy in such a short time? The leading suspects are some of the universe's most extreme objects. One strong candidate is a magnetar, a type of neutron star with a magnetic field so powerful it could strip the information from a credit card from halfway across the solar system. A starquake on the surface of a magnetar, a sudden cracking of its rigid crust, could unleash a titanic blast of radio waves fitting the FRB profile. Another possibility involves collisions or interactions between incredibly dense objects like neutron stars or black holes. The chaotic, energetic aftermath of such a merger could produce a brief, brilliant radio scream as it settles. Yet, even these fantastic explanations have their challenges, especially for the repeating bursts. The precise, focused nature of the emissions and their mind-bending power push the limits of known physics. This inherent mystery opens the door to more speculative and fascinating possibilities. Could FRBs be evidence of alien technology? Some scientists have seriously proposed that bursts of such power and brevity could be signatures of immense light sails, pushed across the galaxy by focused beams of energy. A civilization wanting to propel interstellar spacecraft might use a planet-sized radio transmitter to fire a concentrated pulse, a push that we would see as a blinding, one-time flash as the beam sweeps past our line of sight. An even more expansive idea frames them not as propulsion but as communication. Imagine a vast intergalactic network, a kind of cosmic internet linking civilizations across unimaginable distances. The data packets traveling this network would need to be incredibly energetic to be detectable over billions of light years. An FRB, in this view, could be a fragment of a transmission, a single bit of a message so vast we are only catching a corrupted snippet, a burst of static from a channel we cannot tune into. From the glitch perspective, this is compelling. The sporadic, high-energy, seemingly random nature of fast radio bursts looks less like a natural cosmic process and more like a system error. They are the static pops and bursts you might hear on an old radio when the signal is weak or the wiring is faulty. They are intermittent errors in the cosmic background radiation, sudden spikes of data in the universe's quiet hum. Whether they are the death cries of collapsing stars, the engine signatures of alien vessels, or corrupted packets from a galactic web, their very existence tells us that the cosmos is far from silent. It is a place of sudden, violent whispers, flashes of information we do not yet know how to decode. Each millisecond burst is a reminder that the universe is not just a static picture. It is a dynamic, sometimes chaotic system, and we are only beginning to listen to its strange, sporadic heartbeat. Fast radio bursts are sudden, explosive errors in the cosmic signal. But there is another discrepancy, a quieter and far more fundamental one, that is slowly pulling our model of the universe apart at the seams. It is called the Hubble tension, and it represents a full-blown crisis in cosmology. At its heart, this tension is about a single, crucial number, the Hubble constant. This number tells us how fast the universe is expanding at the present moment. It is the master rate for the entire cosmos, the key to understanding everything from the age of the universe to its ultimate fate. For decades, scientists have worked to pin down this number with ever greater precision. The problem is, two of our most trusted, most rigorous methods for measuring it are now giving us stubbornly different answers. They do not agree, and the gap between them is not shrinking with better data, it is growing. This is not a small margin of error, it is a direct contradiction. The first method looks into the deep past. Scientists use the afterglow of the Big Bang, the cosmic microwave background, as a snapshot of the infant universe. By meticulously studying the tiny fluctuations in this ancient light, they can calculate what the expansion rate should be today, based on our standard model of cosmology, which includes dark matter and dark energy. This method gives us a very precise value. The second method looks at the more recent universe. Astronomers use what are called cosmic distance ladders. They observe pulsating stars known as Cepheid variables in nearby galaxies, whose predictable brightness lets them measure distances accurately. They then look for type 1, a supernova in those same galaxies. Because these supernovae have a known intrinsic brightness, they act as standard candles, allowing scientists to measure distances and expansion speeds across vast stretches of space. This method is also incredibly precise, and it gives a Hubble constant that is significantly faster. The difference is about 9%. One method says the universe is expanding at one speed, the other says it is expanding noticeably faster. Again, this is not about being a little off. It is like having two identical, perfectly calibrated clocks. One, built from the blueprint of the universe's birth, ticks at a steady, predictable rate. The other, set by watching stars explode in the modern cosmos, ticks faster. They cannot both be right if our understanding of cosmic physics is complete. This is the Hubble tension, a persistent glitch in the data that refuses to be smoothed away. So what does this mean? It strongly suggests there is a fundamental flaw in our standard cosmological model, often called lambda CDM. The model might be missing a key ingredient, or one of its core constants might not be so constant after all. Perhaps dark energy, the force driving the acceleration, is not a constant vacuum energy as we assume, but something that evolves over time, growing stronger or changing its properties. This would throw off the extrapolation from the early universe to today. Maybe there is an unknown type of neutrino, or an interaction between dark matter and dark energy we have not accounted for. Some physicists are even considering the possibility that our universe is not perfectly uniform on the largest scales, that we live in a local bubble where the density of matter is slightly lower than the cosmic average, making our local measurements of expansion appear faster. The most profound implication is that we may need new physics. The Hubble tension is a direct challenge, a cosmic anomaly that cannot be explained by simply tweaking the existing model. It points to a crack in the foundation of our understanding, a place where reality itself seems to be disobeying the rules we have written for it. If our universe is a construct, this tension feels like an inconsistency between two subsystems, the physics engine governing the early universe and the one running the present day. It is as if the simulation's expansion parameter was updated in one module, but not properly synchronized with another, leading to a measurable drift between the expected and observed states. This is not just an academic debate. The expansion rate dictates the timeline of the cosmos. A faster expansion means a younger universe. A discrepancy here calls into question the very story we tell about where everything came from and where it is going. The Hubble tension is a quiet alarm bell ringing from the depths of space, telling us that something in our cosmic code is broken. And until we find the bug, our map of reality will remain frustratingly and fundamentally incomplete. The Hubble tension reveals a crack in our cosmic model, but another phenomenon suggests the crack might be the point. This is quantum entanglement, a connection so profound and instantaneous it seems to defy the universe's own speed limit. Picture two particles like electrons created together or interacting in a certain way. They become linked or entangled. From that moment on, no matter how far apart they are separated, their fates remain intertwined. Measure the spin of one particle here on Earth, and its partner, perhaps on the other side of the galaxy, will instantly assume a corresponding spin. This influence happens faster than light, with no signal passing between them. It appears to be a direct, immediate connection across any distance. Albert Einstein, deeply troubled by this implication, famously derided it as spooky action at a distance. He believed it pointed to a flaw in quantum theory, suggesting there must be hidden variables, unknown properties set at the moment of entanglement that predetermined the outcomes. To him, the spookiness was a bug in the logic of the universe. Decades of meticulous experiments, however, have proven Einstein wrong. Entanglement is real. When scientists perform measurements on entangled particles, the results are correlated in ways that no theory of local hidden variables can explain. The particles are not just twins with secret plans, they are a single, unified system that transcends space. This is not a glitch to be patched. It is a fundamental feature of reality, written into the deepest code of the cosmos. The universe at its core is non-local. Things that seem separate and distant to us are, in some essential way, still connected. This has staggering implications. One leading interpretation is the holographic principle, which suggests all the information contained within a volume of space can be represented on its boundary, like a three-dimensional movie encoded on a two-dimensional surface. In such a framework, entanglement is the glue that stitches together this holographic reality. The particles are not communicating across a vast distance. They are adjacent threads on the lower dimensional surface where distance, as we perceive it, is an illusion. From a simulation perspective, entanglement makes perfect sense. In a computer program, two objects can be linked by a common variable or a pointer. Changing the property of one object instantly updates the other because they are not separate entities in storage. They are references to the same underlying data. The spooky action is not action at all. It is simply 2 pixels on a screen reflecting a single change in the code. The vast distance between them is just a rendered effect for the user's experience, not a physical barrier in the processing layer. This view transforms entanglement from a bizarre quantum bug into a potential clue about the substrate of existence. It hints that the separateness we experience, the empty space between stars and between atoms, might be a kind of user interface. The true workings of the universe could be happening on a level where everything is interconnected, where every particle remembers its relationship to every other, bound by invisible threads of information. The spookiness, then, is not in the action, but in the revelation that our classical, localized view of reality is a convenient illusion, a simplified rendering of a far more deeply integrated and mysterious whole. Quantum entanglement reveals a universe stitched together by invisible threads, a reality where separation is an illusion. But there is one place in the cosmos where this delicate quantum fabric seems to be torn to shreds, a place where the fundamental laws of physics face their ultimate test. This is the black hole information paradox, and it represents not just a puzzle, but a catastrophic glitch that threatens to unravel our entire understanding of reality. The story begins with Stephen Hawking's revolutionary insight. Classical physics told us that nothing, not even light, could escape a black hole's gravitational grip. Hawking applied quantum mechanics to the edge of a black hole, the event horizon, and discovered something astonishing. He showed that black holes are not entirely black. Due to quantum fluctuations in the empty space around them, they slowly emit a faint glow of radiation, now called Hawking radiation. This process causes the black hole to lose mass and, over astronomical timescales, to completely evaporate, vanishing from the universe. This was a triumph of theoretical physics, but it came with a devastating consequence. According to quantum mechanics, information is never truly destroyed. If you burn a book, the ashes and smoke still contain, in principle, all the information needed to reconstruct it. The information is scrambled, but it is conserved. Hawking's calculation suggested something different. Imagine you throw a book, a car, and a collection of old hard drives into a black hole. All that matter and information crosses the event horizon and is crushed into the singularity at the center. Later, as the black hole emits Hawking radiation and evaporates, all that comes out is a featureless, random thermal glow. According to Hawking's math, that final burst of radiation contains no trace of what fell in. The information about the book, the car, the hard drives is permanently erased from the universe. This is the paradox. Quantum mechanics says information must be preserved. General relativity, combined with Hawking's work, says black holes destroy it. Both theories are pillars of modern physics, yet they give mutually exclusive answers about how the universe works. It is a direct conflict, a software crash in the cosmic operating system. For decades, this paradox stood as the deepest problem in theoretical physics. If Hawking was right, then our understanding of quantum mechanics is fundamentally flawed, and the universe has a built-in delete function. Physicists have spent years trying to debug this glitch, and their proposed solutions are as mind-bending as the paradox itself. One of the most promising ideas brings us back to the holographic principle. It suggests that all the information about what falls into a black hole is not lost inside it, but is instead encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across the surface. The three-dimensional interior we imagine is a projection of that data. When the black hole evaporates, this information is slowly and chaotically released in the Hawking radiation. It is scrambled beyond easy recognition, like shredding a document and tossing the pieces into a hurricane, but in principle it is still there. Another radical proposal is the firewall hypothesis. It argues that to preserve information, the event horizon cannot be the smooth, uneventful space predicted by general relativity. Instead, it must be a wall of blazing high-energy particles, a literal firewall that incinerates anything crossing it. This would prevent information from ever falling into the black hole in the first place, solving the paradox by dramatically rewriting our picture of what a black hole actually is. These are not just abstract debates, they are active attempts to patch a critical bug in our laws of physics. The information paradox forces us to choose, to find where our theories break down and invent new ones that can reconcile a universe where black holes exist with a universe where information is sacred. It is a glitch that, if unresolved, could mean our entire framework for reality is incomplete. Solving it is not about saving information, it is about saving our understanding of the cosmos itself. Black holes threaten to erase information, but another anomaly suggests the universe might have been born with a flaw in its very blueprint. This mystery lies in the oldest light we can see, the cosmic microwave background, and it carries a disturbing name, the axis of evil. The cosmic microwave background is the faint afterglow of the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. It is the most perfect blackbody radiation we have ever measured, a nearly uniform sea of microwaves bathing the entire cosmos. This uniformity is the bedrock of modern cosmology, evidence for the cosmological principle, which states that the universe is homogeneous and isotropic. In simpler terms, it should look the same in every direction, with no special place and no preferred axis. But when scientists created exquisitely detailed maps of this ancient light using satellites like Oumuamua and Planck, they noticed something unsettling. The tiny temperature fluctuations in the map, the seeds of future galaxies, were not completely random. They showed a strange statistical alignment, a correlation of patterns that seemed to point along a particular axis in space. It was as if the universe had a subtle but definite orientation from its very first moments. This alignment was dubbed the axis of evil, a name reflecting how profoundly it violates our standard assumptions. Its existence suggests the early universe was not perfectly uniform. It had a preferred direction, a cosmic north if you will, which challenges the foundational idea that there is nothing special about our location or perspective in the cosmos. The implications are staggering. If this axis is real and not an illusion, it means the universe might have a large-scale structure or rotation we are unaware of, a primordial twist imprinted at birth. Some theories even suggest it could be a sign our universe collided with another bubble universe in the multiverse during its inflationary phase, leaving a bruise on the sky. The scientific community is deeply divided on what this means. Many argue it is simply a statistical fluke. When you analyze a massive dataset, you can sometimes find patterns that look significant purely by chance. Others have investigated potential systematic errors, subtle biases in the instruments, or in the way we subtract the foreground glow of our own Milky Way galaxy. Yet, despite rigorous checking, the anomaly persists in the data. It refuses to be smoothed away. This leaves the third, most provocative possibility, that the axis of evil is a real feature, a genuine crack in the cosmological principle. It would be a fundamental glitch in the initial conditions of our universe, a sign that the cosmos is not as isotropic and simple as we hoped. From a simulation perspective, this feels like discovering an artifact in the first frame of a rendered video. The background radiation is the startup screen of the universe simulation. A perfect, uniform screen would indicate clean, unbiased code, but an axis, a preferred direction, suggests the initial parameters were not set to a perfectly random state. There might be a coordinate system, a reference frame built into the simulation's foundation that we are not supposed to notice. The axis of evil remains one of cosmology's great unresolved whispers. It is a pattern in the static that may be nothing, or it may be the first clue that our universe has a hidden architecture, a silent axis around which all of creation subtly turns. A glitch in physics so tempting it promised to rewrite the textbooks. For years, a small, controversial device known as the M drive, or electromagnetic drive, captivated engineers and dreamers alike. Its claim was simple and utterly revolutionary. It seemed to generate thrust without any propellant. No burning fuel, no expelled ions, no reaction mass of any kind. You would simply pump microwaves into a sealed, asymmetrical metal chamber, and the whole apparatus would push gently in one direction. On paper, this was impossible. It directly violated Newton's third law, the foundational principle that for every action there is an equal and opposite reaction. Rockets work by throwing mass backward to go forward. The M drive proposed to move forward by doing nothing more than bouncing energy around inside a box. It was the physics equivalent of a car moving by pushing on its own dashboard. Yet for over a decade, several experimental teams, including a respected group at NASA Eagleworks Laboratory, reported measuring a tiny but persistent thrust. The numbers were small, mere micronewtons, but if real, the implications were universe-altering. It hinted at a loophole in the laws of motion, a way to propel spacecraft across the solar system without carrying vast tanks of heavy fuel. The dream of efficient, fast interplanetary travel suddenly seemed within reach. The scientific community, however, met these claims with profound and healthy skepticism. Extraordinary claims require extraordinary evidence, and a violation of conservation of momentum is about as extraordinary as it gets. Critics pointed out the minuscule forces measured were deep within the realm of experimental error. Could the thrust be an artifact, an illusion created by the experiment itself? The long, meticulous process of debugging this tantalizing glitch began. Researchers worldwide scrutinized the setup. They considered the interaction of the device's power cables with Earth's magnetic field. They examined thermal expansion, the simple idea that as the metal chamber heated up from the microwaves, it could expand unevenly and impart a tiny push. They built more sophisticated test rigs, including one that suspended the M drive in a vacuum chamber to eliminate air currents. For a while, the signal persisted, a ghost of thrust that refused to vanish. The turning point came with increasingly precise experiments designed to isolate and kill every possible error. One by one, the phantom thrusts were traced back to mundane sources. In some tests, the measured force was linked to the thermal interaction between the device and the scale used to weigh it. In others, it was an electromagnetic interaction with the test facility's environment. The most definitive blows came when researchers built control experiments using devices that should not, by any proposed theory, produce thrust. When these null tests, these scientific placebos, also showed apparent thrust under the same conditions, the conclusion became inescapable. The thrust was not coming from a new physics. It was a measurement error, a subtle, systematic bias that had fooled multiple teams. The M drive as a reactionless engine was debunked. But this story is not a failure of science. It is a case study in science working exactly as it should. a strange signal appears, a potential glitch in reality's code. It is investigated with hope but also with ruthless rigor. Alternative explanations are hunted down. The experiment is tortured until it confesses the truth. What remains is not disappointment, but a clearer, more reliable map of how the universe actually works. The dream of a free lunch in propulsion faded, but our process for separating wishful thinking from physical law was proven stronger than ever. The dream of a propellantless engine faded under scrutiny, but the universe soon delivered a mystery that required no engine at all. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint point of light moving at breathtaking speed. Its trajectory was unlike anything seen before, a hyperbolic path that screamed it was not from here. This was Oumuamua, the first known interstellar object to visit our solar system. Its name, from Hawaiian, appropriately means scout or messenger from the distant past. It was a cosmic interloper, a glitch in the predictable clockwork of our local system. The data revealed an object utterly alien in its properties. First, its shape. Based on how its brightness changed dramatically as it tumbled, scientists deduced it was highly elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or a flattened pancake. Nothing in our solar system, no asteroid or comet, naturally forms in such an extreme shape. Second, and more perplexing, was its motion. As Oumuamua sped away from the sun, it did not follow a purely gravitational path. It exhibited a small but clear additional acceleration, as if being gently pushed. For comets, such a push is common, caused by outgassing, when solar heat vaporizes ice and the escaping jets act like tiny thrusters. But Oumuamua showed no visible coma, no tail of gas and dust that telescopes could detect. It was accelerating in silence and in darkness. This was the core of the mystery, a glitch in the orbital mechanics. The scientific community scrambled for explanations. One compelling natural theory proposed it was a hydrogen iceberg. In the cold depths of interstellar space, a chunk of solid molecular hydrogen could form. As it neared the sun, the hydrogen would sublimate, providing the unseen push for acceleration and leaving no dusty trail for our instruments to see. Another leading idea suggested it was a fragment of a nitrogen ice shell, perhaps from a Pluto-like world in a distant solar system, chipped off in a cataclysm. The nitrogen would also sublimate cleanly, explaining the thrust. Yet these theories, while elegant, had to stretch to fit all the data perfectly. The hydrogen iceberg, for instance, might not survive the long journey between stars. The absence of any visible outgassing remained deeply puzzling. Into this uncertainty stepped a more sensational hypothesis. Could Oumuamua be artificial? Astronomer Avi Loeb famously proposed it might be a light sail, a thin sheet of material designed to be pushed by the radiation pressure of starlight. Its unusual shape would be ideal for such a function, and its acceleration without visible outgassing could be explained by sunlight itself pushing on a large, thin, lightweight object. It could be a discarded piece of advanced technology, a derelict probe, or an active explorer from another civilization sailing the galactic currents. This idea captured the public imagination, framing Oumuamua not as a rock but as an artifact. From our glitch in reality perspective, this interstellar visitor is a perfect example of an anomalous data packet. Our solar system is a well-modeled environment with predictable rules for asteroids and comets. Then, a single object enters the system, breaks several of those rules with its shape and its silent acceleration, and exits before we can get a close look. It is a transient error in the local simulation, a signal from an unknown cosmic process that we observed only in passing. Whether it was an exotic shard of a distant planet or a piece of alien engineering, its true nature is now forever lost to the void. Oumuamua is gone, speeding back into the interstellar dark. It serves as a humbling reminder that our cosmic neighborhood is not a closed system. Occasionally, something from the outside slips in, behaves strangely, and challenges everything we think we know, leaving behind only questions and a faint trail of data in its wake. Oumuamua was a silent visitor, a fleeting anomaly that defied our categories. But what if a glitch could be triggered not by an object's strange properties, but by the simple, persistent act of looking? This brings us to one of the most mind-bending predictions of quantum theory, the quantum Zeno effect. It proposes a truth so counterintuitive it feels like a cheat code for reality, that an unstable system can be prevented from changing simply by observing it frequently enough. The classic example involves an unstable particle, one that is poised to decay, to transform into something else. Left to its own devices, it will do so within a certain predictable time frame. But according to the quantum math, if you repeatedly and rapidly measure this particle, asking it over and over again if it is still in its initial state, you can effectively freeze it in place. The constant barrage of measurements resets the particle's internal quantum clock, stifling its natural evolution. The analogy is the old saying, a watched pot never boils. Of course, in our macroscopic world, staring at a kettle does not affect the water molecules, but in the quantum realm, observation is not a passive act, it is an intervention. Each measurement forces the system to choose, to collapse from a probability cloud into a definite state. By measuring it continuously, you are essentially pinning it down, preventing it from exploring the possibility of decay. It is a bizarre glitch where the tool we use to understand reality, measurement, becomes a tool to control it. This has been demonstrated in laboratories. Scientists have used lasers to repeatedly observe atoms in an excited state, and by doing so, they have significantly delayed those atoms from dropping back down to a lower energy state and emitting light. The system was literally talked out of its natural behavior by being watched. The philosophical implications are profound. It blurs the line between observation and creation. If continuous observation can lock a quantum system into a particular state, what does that say about the role of a conscious observer? Could a universe that is constantly being observed or measured in some fundamental way be a universe that is being held in a particular configuration? It is a dizzying thought that reality might require a kind of persistent attention to maintain its familiar structure. From our glitch perspective, the quantum Zeno effect looks like a system latency issue. In a simulation, a process that is not being actively rendered or queried might remain in a low-resolution state or even pause to save resources. But the moment a user focuses on it, the system prioritizes that process, calculating its state in detail. If the queries come in a relentless, rapid-fire sequence, the system might get stuck in a loop, constantly updating the object's present status and never getting the processing cycle to calculate its next natural transition. It is as if the universe's processor is so busy answering the question, "Are you still there?" that it never gets to the command, "Now change." This effect suggests that at its core, reality is not a continuous movie, but a series of still frames, and the rate at which those frames are refreshed or observed can determine what happens next. It turns a fundamental principle of our experience, that time flows forward, into something that might be contingent, something that can be slowed or even suspended by the very act of witnessing it. The quantum Zeno effect shows how observation can freeze reality, but what if the fabric of spacetime itself contained tiers and backdoors? Einstein's equations of general relativity, which so beautifully describe gravity as the curvature of spacetime, also contain strange and speculative solutions. These are not observed phenomena, but mathematical possibilities, glitches in the very geometry of the cosmos. The most famous are black holes, regions where gravity is so intense that nothing can escape. But the math also describes their theoretical opposite, white holes. If a black hole is a one-way street where matter and light can only fall in, a white hole is its time reversal, a cosmic exit where matter and energy can only spew out. Nothing can enter a white hole. It would be a fountain of radiation and matter erupting from a single point in space, a source with no apparent origin. Think of it like a video of a black hole playing in reverse. While black holes are thought to form from collapsing stars, there is no known physical process that would create a white hole. They exist purely as a mathematical curiosity, a potential glitch in the system where the universe's normal rules of entry and exit are flipped. Then there are wormholes, perhaps the most tantalizing idea of all. Formerly known as Einstein-Rosen bridges, these are hypothetical tunnels through the fabric of space-time. Imagine the universe as a vast sheet of paper. To get from point A on the left side to point B on the right side, you would have to travel all the way across the sheet. But if you could fold the paper so that points A and B touched, and then pierce through the fold, you would create a shortcut, a tunnel connecting two distant regions. That is a wormhole, a cosmic shortcut that could, in theory, connect places billions of light years apart or even different points in time. In science fiction, they are the ultimate plot device, enabling instantaneous travel across the galaxy or journeys into the past and future. They are the stargates and hyperlanes of countless stories. From the perspective of a glitch in reality, both white holes and wormholes feel like profound errors or hidden features in spacetime's code. A white hole is like a bug in the gravitational software where an output valve has gotten stuck in the open position, violently ejecting everything. A wormhole is a backdoor, a cheat code that bypasses the normal, slow travel protocols of the universe. It is a rendering shortcut where two distant points are linked directly, skipping the need to calculate everything in between. The catch, and the reason we have never observed one, is that these structures are almost certainly unstable. According to our best models, a wormhole would collapse instantly under its own gravity the moment it formed, pinching shut before even a single photon could shoot through. To hold it open, you would need something with negative energy density, a kind of exotic matter or energy that repels gravity itself. We do not know if such a substance can exist in reality. So these remain hypothetical, mathematical specters in Einstein's equations, yet their persistence in theory is a powerful reminder. Our understanding of gravity allows for these bizarre possibilities. It suggests that spacetime is not a rigid, immutable stage, but a dynamic, twistable medium that could, under the right conditions, be punctured, folded, or reversed. They represent the ultimate limits of our physical models, places where the map of reality hints at wonders and shortcuts that may be forever just out of reach or waiting to be discovered in the deeper layers of the cosmic code. Mathematical shortcuts like wormholes challenge the geometry of space, but a far stranger idea questions the very nature of existence itself. This is the Boltzmann brain paradox, a thought experiment so unsettling it suggests the most fundamental glitch might not be in the universe, but in our own sense of self. It begins with a simple, well-established principle of thermodynamics that systems tend toward disorder, toward a state called entropy. Given enough time, in an eternal and infinite universe, even the most chaotic, high-entropy state will experience random fluctuations. Most of these fluctuations are tiny, a few atoms bumping together, but given infinite time, even the most wildly improbable event will eventually happen by pure chance. This includes the spontaneous assembly, from the random jostling of particles in a complete vacuum, of a fully formed, self-aware human brain, complete with a lifetime of detailed, coherent memories. This phantom consciousness would pop into existence, believe itself to be a person living in a real world, think for a moment, and then immediately dissolve back into the chaos. It is the ultimate accident of existence, a cosmic hiccup of awareness. The paradox arises when we apply this logic to our own situation. We believe we are the result of billions of years of orderly cosmic evolution, living in a low-entropy universe that began with the Big Bang. But from a statistical standpoint, it is infinitely more likely for a single, disembodied brain to fluctuate into existence with false memories of a past than for an entire ordered universe with galaxies, planets, and billions of real people to form spontaneously. So the chilling conclusion of the paradox asks, which scenario are we actually in? Are we the legitimate products of a long, structured cosmic history, or are we, right now, momentary Boltzmann brains, just hallucinating a universe around us for a fleeting instant before we blink out of existence? This is not just a philosophical puzzle, it is a direct challenge to our cosmological models. If our theory of the universe predicts that Boltzmann brains should be more common than ordinary observers like us, then that theory is almost certainly wrong, or at least incomplete. Scientists work to construct models of cosmic inflation and dark energy that avoid this fate, that ensure stable, long-lasting universes where real observers are the norm, not the absurdly rare statistical fluke. The idea feels like the ultimate system error. If reality is a vast, chaotic simulation running on autopilot, a Boltzmann brain is a corrupted process, a brief spike in the random noise that mistakenly generates a subroutine of self-awareness. It is a ghost in the machine, a consciousness without a cause, experiencing a phantom reality that has no external referent. It forces us to confront a terrifying possibility. The solid ground of our past, our memories, and the world we perceive could be an illusion generated by a random accident in an endless, mindless void. Our deepest certainty that we are real beings in a real cosmos becomes the very thing we cannot prove. The Boltzmann brain paradox is the glitch that undermines every other glitch because it suggests the anomaly might not be out there in the stars, but right here, in the fragile sense of being that is asking the questions. The most profound glitch may not require a telescope or a particle accelerator to witness. It happens in doctors' offices every day, a phenomenon where a sugar pill can cure a headache, reduce pain, or even improve Parkinson's symptoms simply because the patient believes it will. This is the placebo effect, a direct and measurable demonstration that our expectations can rewrite our physical reality. It is not just in our heads, it is in our bodies, altering brain chemistry, immune responses, and nervous system activity. In rigorous studies, patients given sham surgeries for knee pain often show the same level of improvement as those who received the real procedure. The belief in the treatment activates the body's own innate healing systems, releasing endorphins and modulating inflammation. The mind is not a passive observer of the body, it is an active participant in its state of health. This human-scale mystery echoes the quantum strangeness we explored earlier. Just as observing a particle seems to force it into a definite state, our conscious expectations appear to nudge our biological systems toward a specific outcome. The act of belief, of focused expectation, functions like a command line input. It does not create healing from nothing, but it directs and amplifies the body's existing latent capacities. This suggests our conscious mind might be far more than a byproduct of brain chemistry. It could be a localized interface, a user experience portal through which we interact with and influence the underlying system of our physical being. We are not just reading the data of our reality, we are issuing commands that the system obeys within certain limits. The placebo effect reveals that the boundary between mind and matter is porous. Our expectations are not mere thoughts, they are tools that can recalibrate pain thresholds, shift immune markers, and alter disease progression. This is not magic, it is a reproducible scientific fact that highlights a stunning glitch in the standard model of biology. If our focused attention can heal a wound or calm an allergic reaction, what does that say about the true nature of our consciousness? Perhaps we are not passive passengers in a mechanical universe, but active users with a degree of administrative access, learning through trial and error how to issue the commands that shape our most immediate reality. The placebo effect reveals how our expectations can bend physical reality. But what about those moments when the external world seems to bend to meet our thoughts? This is the realm of synchronicity, a concept defined by psychologist Carl Jung as a meaningful coincidence and a causal connecting principle. It is when an event in the outer world mirrors an inner thought or feeling with such precision and timeliness that it feels like more than mere chance. You think of a long-lost friend, and a moment later they call. You hear a rare word for the first time, and then it appears 3 times in the same day. You have a dream about a specific symbol, and the next morning you encounter it on a stranger's shirt. These are not linked by cause and effect, but by meaning. They feel like glitches in the normal, linear flow of time and causality, moments where the universe seems to wink at you. Jung proposed that synchronicities point to a deeper, unified reality beneath the surface of our fragmented world, a layer where mind and matter, the psychological and the physical, are not separate but intertwined. In this view, the coincidences are not random noise, but meaningful patterns emerging from a holistic cosmos, like ripples on a pond that connect distant points without a direct push. From a purely statistical standpoint, with billions of thoughts and events happening every second across billions of people, some astonishing coincidences are bound to occur. Our brains are pattern recognition machines, wired to find meaning and often ignoring the countless non-coincidences to highlight the one that strikes a chord. In a vast and busy universe, sheer probability guarantees that seemingly miraculous alignments will happen. Yet, for the person experiencing it, the statistical explanation often feels hollow. The emotional weight, the uncanny timing, the deep personal relevance, these elements defy cold numbers. It feels less like rolling dice and more like receiving a message. Could these be subtle signals from a universe that is not just a collection of objects but possesses narrative elements? Some interpretations suggest that in a simulated reality, synchronicities could be user feedback, a way the system responds to our internal state, nudging us along a particular path or validating a decision. They might be gentle corrections in the code, aligning environmental variables with our conscious or subconscious queries. Others see them as evidence of the interconnected web suggested by quantum entanglement, manifesting not just in particles but in the macro-scale events of our lives. Whether they are statistical ghosts or genuine glimpses of a connected whole, synchronicities challenge our model of a purely mechanical universe. They introduce the possibility of meaning as a fundamental force, a glue that binds events together in ways that physics cannot yet describe. They are the soft, personal glitches that suggest our story might be interwoven with the story of everything else in ways we are only beginning to sense. History itself might not be as solid as the textbooks suggest. There exists a fringe theory known as the phantom time hypothesis, which proposes a startling glitch in our collective past. It argues that nearly 300 years of history, specifically the period between 614 and 911 AD, never actually happened. According to this idea, these centuries were either invented out of whole cloth by later rulers and scholars, or were the result of a massive, systemic error in dating historical events. The architect of this theory, a German historian named Herbert Illig, suggested that the early Middle Ages were artificially extended. He pointed to a perceived scarcity of reliable archaeological evidence from this period in Europe, inconsistencies in architectural styles, and what he saw as suspiciously neat chronological calculations by medieval scribes and the church. The motivation, he proposed, was political. By inserting these phantom years, rulers like the Holy Roman Emperor Otto III could align their reign with the year 1000 AD, a momentous millennial date that would bolster their authority with a sense of divine destiny. The theory also looks to dendrochronology, the science of dating using tree rings. Proponents once pointed to gaps or ambiguities in long-term tree ring records that seemed to make it difficult to create an unbroken sequence back through that specific era. They argued this was not an accident of preservation, but a sign the years themselves were missing. While captivating, the phantom time hypothesis has been overwhelmingly rejected by mainstream historians, archaeologists, and scientists. The dendrochronological evidence, once cited as support, has now been solidified. Researchers have constructed continuous tree ring sequences that stretch back over 11,000 years, using samples from ancient wood, fossilized trees, and even timber from Roman ships. These sequences show no missing centuries. They interlock perfectly, providing a robust, natural calendar that confirms the traditional timeline. Furthermore, the archaeological record, while less dense in some regions than others, is far from empty. Coins, buildings, manuscripts, and records from civilizations outside of Europe, like the Byzantine Empire and the Islamic Caliphate, which meticulously documented astronomical events and their own histories, provide a consistent, cross-referenced timeline that leaves no room for a 300-year vacuum. So why does this debunked idea still fascinate us? Because it taps into a deep-seated vulnerability in our understanding of reality. Our history is a story we tell ourselves, pieced together from fragments. The phantom time hypothesis is a powerful thought experiment that forces us to confront the constructed nature of our timeline. It asks, what if the narrative is wrong? What if there are gaps not of years but of understanding, where our records failed and our assumptions filled in the blanks? While the specific 300 years are almost certainly real, the theory serves as a metaphor for the fragility of human memory on a civilizational scale. It reminds us that our past is not a fixed recording but a continuous act of interpretation, and that the ground beneath our feet, even the historical ground, might have more cracks and seams than we comfortably assume. These strange whispers from the cosmos, from our own minds, and from the edges of physics are not proof that reality is broken. They are invitations. For every tantalizing glitch, from the wow signal to the flicker of Tabby's star, humanity has developed a powerful, self-correcting tool for investigation, the scientific method. This is not a dry set of rules. It is our species' debugger, the process we use to separate signal from noise, wishful thinking from physical law. It begins with an anomaly, a measurement that does not fit, a memory that feels wrong, a star that dims oddly. That spark of curiosity is essential, but it is only the start. The true work lies in the rigorous, often unglamorous pursuit of an explanation, a pursuit built on two pillars, skepticism and reproducibility. Healthy skepticism is not cynicism, it is a protective layer. When we hear of a reactionless engine or a signal from aliens, the first question must always be, what else could it be? Could it be an instrument error, a thermal effect, a statistical fluke? This forces us to challenge our own assumptions and desires. The M-Drive story is a perfect testament to this process, where initial excitement was ultimately tempered by meticulous experiments that hunted down every possible mundane cause. The anomaly was not ignored, it was interrogated until it confessed the truth. Then comes reproducibility, the gold standard. A single, strange event is a mystery. A strange event that can be predicted and observed again under controlled conditions moves toward being a new fact of nature. The quantum Zeno effect is not just a wild idea, it is a laboratory reality demonstrated repeatedly. The Mandela Effect, while powerful, struggles with this test as we cannot reliably reproduce a change in reality on demand. This process is how we patch our understanding. Each confirmed glitch that withstands scrutiny, like quantum entanglement or the accelerating expansion driven by dark energy, forces us to expand our models. We do not throw out the old code, we debug it. We write new subroutines that account for the new data. The Hubble tension is not a failure. It is the system currently highlighting a critical inconsistency in our cosmological software, directing brilliant minds to find the missing line of code. This journey requires a delicate balance, a blend of open-minded imagination and ruthless critical thinking. We must be willing to consider the extraordinary, from alien megastructures to simulated realities, but we must also be prepared to let those ideas go if the evidence does not support them. Celebrating the mystery is just as important as solving it, because the pursuit itself is what propels us forward. Every unexplained signal, every paradoxical particle, every silent sky is a question waiting to be asked, and it is in the asking, in the tireless debugging of reality, that we truly discover not just how the universe works, but what it means to be a conscious part of it, forever curious, forever testing the limits of the world we perceive. From quantum particles that know when they are watched to silent galaxies that should be shouting with life, this journey has taken us across a landscape where reality itself seems to flicker. We have seen stars that dim without cause and signals that vanish without a trace. We have grappled with the possibility that our universe might be a construct, a simulation running on cosmic hardware we cannot perceive. Each anomaly, from the Mandela Effect shared memories to the stubborn tension in the universe's expansion rate, is more than a simple error. These are not failures of the system, but its most fascinating features. They are clues etched into the fabric of everything, hints that our current understanding is a map, and the territory is far wilder than the map shows. The glitches are the places where the map is frayed, where the light of our curiosity shines through and shows us there is so much more to explore. They remind us that mystery is not an obstacle to knowledge, it is the very ground from which knowledge grows. So we turn the question to you: which of these glitches in reality resonates most deeply with your own experience? Is it the eerie silence of the Fermi paradox, or the personal, uncanny jolt of a synchronicity? Share your thoughts in the comments below. If you are captivated by these deep dives into the unknown, consider subscribing to stay connected. Together, we can keep questioning, keep exploring, and keep our eyes wide open for the next crack in reality, the next whisper from the universe that tells us the story is far from over.